Hello folks, today we are starting with a new series on heaps, or more specifically binary heaps. This video will mostly focus on the concept of heaps, and we'll also discuss the advantages of using a heap, its implementation, visualization, and finally the time complexity for different operations. In the subsequent videos, we will focus on some good lead code problems based on the concept of heaps. So without any further ado, let's get started with our discussion. Heap is a very interesting data structure in the sense that it is a tree based data structure, or it is visualized as a tree, but it is actually implemented as an array. So, for a while, till we reach the implementation part, we will be visualizing it only as a tree. And once we reach that part, we'll discuss how it is actually implemented as an array. For any binary tree to be called a binary heap, it needs to follow two properties. So these are two mandatory properties. The first property is that the binary tree needs to be a complete binary tree. Now, what is the definition of a complete binary tree? For a tree to be called a complete binary tree, all levels in the tree should be completely filled except the last level, and all the nodes in the last level should be as left as possible. Now let's try to look at few examples, and let's try to understand this. So these are the first two examples. Now we can see that both of these trees are binary trees because each node has two or less number of children. And let's try to see that whether these two trees are complete binary trees or not. So we know that our definition of complete binary tree tells us that all levels in a binary tree should be completely filled except the last level. And we can see that this is the last level of this binary tree. This is the last level, and we can see that this level is not completely filled because this node has two children, and that's why this is complete, but this node is not having its two children. So this particular level is not completely filled, and this is not the last level as well. So hence we can say that this tree is definitely not a complete binary tree. Again, in this example, we can see that this is the last level. So this is the last level, and all the levels above this level are completely filled. So this level is completely filled, this level is completely filled. But again, our definition says that even in the last level, all the nodes should be as left as possible. So these two nodes, particularly these two nodes, are not completely on the left side. So for these nodes to be completely on the left side, these should have been children of this particular node. So since this level is missing the children for this particular nodes, all the nodes in the last level are not completely on the left side. Hence again, this is not a complete binary tree. Now let's look at the next examples. So again, in this tree, this is the last level. So all the levels before the last level are completely filled. Yeah, they are. But again, the nodes in the last level are not completely on the left side. So again, this node is missing, which is the leftmost node. That's why again, this tree is not a complete binary tree. Again, this is the last level, but this node should have been here. So we are missing this node. So again, we can say that in this tree, all the nodes are not on the leftmost side. And again, that is why this is not a complete binary tree. Now let's look at this last example. So we know that this is the last level. So all the levels above this last level are completely filled. So we have this node, we have this node, this is also there, this node is also there, this node and this node. We are not missing any node. And all the nodes on the last level are as left as possible. So moving from left to right, we are not missing any node. All the nodes are present, and after the first missing node, which is this node, there are no more nodes. So all the nodes are as left as possible. So yeah, this is a complete binary tree. So now that we have understood the first property, let's try to understand the second mandatory property. To understand the second property, we need to know that there are two kinds of heaps, a max heap and a min heap. In a max heap, value of a node needs to be greater or equal to the value of both of its immediate children. And this property is true for every node in the heap. In a min heap, value of a node should be less than or equal to the value of both of its immediate children. And again, this property is true for every node in the heap. Let's again look at a few examples. So in our first example, we can see that the value of every node is greater than both of its immediate children. So this is 9 and its immediate children are 8 and 3, and 9 is greater than 8 and 3, so this node is following that property. Now again for 8, its only child is 7 and 8 is greater than 7, so again this node is also following the property. Again for 3, its children are 1 and 2, and 3 is greater than both 1 and 2, so again 3 is also following the property. So this particular heap is following all the properties of a max heap, since the value of every node is greater than its immediate children. But this tree is somehow not a complete binary tree, because the nodes on the last level, which is this particular level, are not on the leftmost side. So we are missing this particular node. If we start traveling from left to right, we'll find a missing node. So that's why this particular tree does not follow the first property, and hence it is not a heap. In our next tree, this particular tree is following the property of min heap. So in this, every node is smaller than its immediate children. So the root node, which is 1, is actually smaller than both of its children, that are 3 and 6. So this is following the min heap property. Again, 3 is smaller than 8 and 4, so 3 is also following the property, and 6 is smaller than 7. Now this particular tree is also following the first property, because this is a complete binary tree. We are not missing any node when we start moving from left to right on the last level. Therefore this tree can be called a heap, and the type of heap this tree is, it is a min heap, because every node is smaller than its immediate children. Now again, in this last example, we can see that it's a complete binary tree, so it is following the first property, and all the nodes are greater than their immediate children. So this particular tree is a heap, and the type of this heap is max heap, because all the nodes have a value greater than their immediate children. Now why it is mandatory for a heap to follow these two properties? The first property is the reason why we are able to implement heaps as an array, and you'll see this in just a few more minutes, that how this property is ensuring that we are able to implement it as an array. And the second property ensures that the smallest number in the min heap is at the root, and the greatest number in a max heap is at the root. So what is the value added by this? Now imagine that you had a tree or an array. To find the smallest element, you would have to traverse the complete array as well as tree. That would have taken big O of n time. But in a min heap, since the min element is always at the root, you can find the min value in just big O of 1 time. Pretty sweet, right? So also imagine that you need to remove the minimum element. Again, in an array or a regular binary tree, you would have taken big O of n time in just finding the element. But in heaps, we can remove the minimum element in just big O of log n time. So we will discuss this time complexity in detail shortly, but you can see that how this heap helps us, or is a great improvement in locating the minimum element as well as removing the minimum element from the collection. And similarly for max heap, finding the greatest element and removing the greatest element. Now before moving any further, let's understand two very important operations on heap. These operations are used while inserting and deleting elements from a heap. So having a good understanding of these operations will make understanding insertion and deletion very easy. The first operation is the Heapify operation. This operation helps us in taking the root to its correct position in the heap. So for instance, we have a min heap and the value in root is not the smallest value in the tree. So it is not in its correct position. And let's assume all other nodes are in their correct position. So we need to transfer that value to its correct position, right? We do that using the Heapify operation, which is a recursive operation. Let's understand using an example. We can see that this tree is a complete binary tree, and all nodes except the root are following the min heap property. If we are able to take 60 to its correct position, we will get a perfect min heap. Now I'm explaining Heapify for min heap, but the logic will remain exactly same for max heap, just every step would be depending on the greatest value. In Heapify, what we do is that if the current node is not smaller than both of its children, we swap it with the smallest child and then call Heapify on that child. By doing this, what we have done is that we have satisfied the heap property for the current node and we have delegated the same task to the child to satisfy heap property for itself. The child will do the same operation and in turn pass on the responsibility to one of its own child. So let's dry run this on the example and then it'll become much more clear. Now 60 is definitely not smaller than 15 and 11. So definitely heap property is not satisfied because we are trying to make a min heap. Now what we need to do is replace 60 with one of its child. Now we cannot swap it with 15, right? Let's try to understand why. Because if we swap 15 and 60, the tree would look something like this. And we can see that even after the swap, 15 would be greater than its child 11 and again heap property would not be satisfied. So it does not make sense to swap 15 and 60. So it always makes sense to swap the parent with the smallest child. So now we will swap 60 with 11. So our tree would look something like this. Now we see that this current tree is following the heap property, and now what we do is that we delegate this task to the second child to satisfy the heap property for itself. Now you might be getting an idea how this heapify would take 60 to its correct position. So we have delegated this task to 60 and we can again see that 60 is not in its correct position, so 60 will replace itself with 33. So then after this replacement the tree would look something like this. Now again 60 is not in its correct position, it is greater than its children. So we will again replace 60 with the smaller child and the tree would look something like this. Now since this particular node has no children, so obviously Heapify would stop here. And we can see that how after running Heapify on this tree, we have converted it into a min heap because it is a complete binary tree and all the nodes are actually smaller than their immediate children. So the stopping or base condition for Heapify is that when the node has no children or the value in node is already smaller than both of its children. So we have already seen the case where 60 has no more children, so Heapify stops. For instance, if the tree would have been something like this. So in our previous step, 60 was here, and let's assume that the children were actually greater than 60. So let's assume that the children were 100 and 102. So now 60 is smaller than both of these children, so no swap is required. So this is another condition where the heapify stops. Now let's try to understand the time complexity for this operation. In the worst case, heapify will follow exactly one path from root to one of the leaves. So in this current scenario, heapify followed this path. So that means that it will traverse the height of the tree or perform operations equal to the height of the tree. And we know that height of a complete binary tree with n nodes is log n. So the time complexity for our heapify function is actually big O of log n when there are n nodes in the tree. Now the next important operation is taking the last element to its correct position in the heap. So earlier what we did, we took root to its correct position. Now we have to take the last element in the tree to its correct position. And this time let's understand this for a max heap instead of a min heap. In this operation what we do is that if the node is greater than its parent, we swap it with the parent and call the same method recursively for the parent. By doing this, we have satisfied the heap property for the current subtree and we just delegated the task to satisfy this property for itself. So let's take an example and try to understand it better. So And so we also need to remember that all the other nodes are in their correct position. Just the last node is not in its correct position and we need to take it to its correct position. So again, this is a complete binary tree, and I have not drawn some of the left hand side nodes because we have already discussed that all other nodes are in their correct position. So I have just drawn the nodes which are of use to us. Now as we can see that 91 is greater than 53, so we can replace or swap 53 and 91. So after doing that, the tree will look something like this. Now you might wonder that we have swapped 53 and 91, but how does that ensure that 91 will be greater than all the nodes in its left subtree? Because we actually did not check the relation with the other child. So how do we know that the heap property is going to be maintained? To understand this, let's take the small tree ABC and let's assume that C is not in its correct position. So let's assume that C is actually greater than A. So since C is not in its correct position, so it is given that C is greater than A. And again we know that all the other nodes are in their correct position, so A has to be greater than B. So now if we are following these conditions, the final ordering between all these nodes would be that C is greater than A is greater than B. So now since this is the correct ordering between the value of the nodes, we know that why it makes sense to make C as the parent, because C will, once C and A are swapped, the new parent will actually be greater than both the nodes. And subsequently, since B will be greater than all the nodes in its subtree, we know that we have kind of maintained the max heap property. So moving to the original tree, we now replace 91 and 82 because obviously 91 is greater than 82. So after the operation, the tree would look something like this. And now replacement is not possible because 91 is in its correct position, because 91 is actually smaller than 96. So the operation ends here. Again, the stopping condition for this operation is that no swap is possible or needed, or we have reached the root. So again we can see that after this operation the tree has become a max heap, since all the other nodes were already there, and for the remaining nodes now the max heap property is being satisfied and it was always a complete binary tree. So again we know that in the worst case we traverse all the nodes in a path from root to leaf. So for this particular case we have traversed this particular path, and since we are traversing one path from root to leaf, so or from leaf to root rather, so again the worst case time complexity for this operation is going to be big O of log n, where n is the number of nodes in the tree. Now that we have understood these operations, it will be really easy to understand insertions and deletions in a heap. In insertion, what we do is we add the new element as the last node in the current tree and move the last node to its correct position by following the second operation that we discussed above. Let's take an example. So we will create a max heap here. So the given array is 4, 6, 10, 1, 13, and we need to create a heap for this. So first our tree is completely empty and we will enter the first element, that is 4. So since the tree is completely empty, 4 will become the root for this tree. Now what we do is that we add 6 to this tree. So when we add 6 to the tree, obviously since we have to make a complete binary tree, 6 will come as the first child or the left child of 4. Now we know that we are making a max heap and this does not follow the max heap property. So what we do is we call the second operation on this tree. So what second operation does is that it takes the last node to its correct position. So the second operation will take 6 to its correct position and our heap will look something like this. Now we add 10 to this heap. So again 10 will be added as the last node in the heap. So the last node right now is going to be the right child of this node. And again we know that 10 is not in its correct position because we are making a max heap. So we will call the second operation, and second operation will take 10 to its correct position by recursively swapping it with its parent. So our heap would look something like this. Now we add 1 to this heap, so 1 will be added as last node. So last node right now will be the left child of 4, and we can see that 1 is already in its correct position, so we do not need to call the second operation on this. Now what would be the next step? That we would be adding 13 to this heap. So 13 again will be added as the last node. So last node here would be the right child of 4. Now we can see that 13 is not in its correct position, so we have to take 13 to its correct position. So how will we do that? We'll do that by swapping 13 with its parent. So this will kind of become 4 and this will become 13, and we will call that second operation recursively for the new parent. We again see that this is not in its correct position, so it will be swapped with its parent, and 13 will reach here and 10 will come here. So our final heap would look something like this. And as you can see that using just the second operation, we have created our max heap. Now let's try to analyze the time complexity for creating a heap. We can assume that adding the last node or removing the last node takes big O of 1 time in our array implementation. This will be clear really soon, but let's assume for now. Now the only costly operation is taking the node to its correct place. And we already know that the cost of that operation is big O of log n, where there are already n nodes in the tree. So we can say that adding first node is going to take big O of 1 time because there are no nodes in the tree. Then adding second node will take big O of log 1 time. Why? Because adding the node takes big O of 1 time and taking it to the correct position takes log n time. And since the height of the tree is only 1 because there's only one node in the tree, so adding the second node takes big O of log 1 time. Similarly, adding third node will take big O of log 2 time, and similarly so on. Adding nth node will take big O of log of n minus 1 time. Now what would be the total time complexity of making heap? It would be just the sum of all these time complexities. Now let's try to come up with an upper bound for this series. The sum of this series will be definitely less than log n plus log n times, right? Because 1 plus log 1 plus log 2 till log n minus 1 will definitely be smaller than log n plus log n plus log n n times, and we can say that this will be less than n log n. So we can say that n log n will be the upper bound for this series. This is the reason a lot of resources mentioned that the time complexity for building a heap is big O of n log n, because big O time complexity is nothing but a asymptotically tight upper bound. So this might sound right, but actually this is not at all asymptotically tight. Like by this logic we can say that big O of n square is the upper bound. It is, but that is a very wrong estimation, because anything greater than n log n will also be a upper bound for this series, but we cannot say that the time complexity will be big O of n square, because big O of n square will actually be really higher than the actual time complexity. So by some hardcore mathematics we can prove that the asymptotically tight upper bound for this particular series is actually big O of n. So the time complexity for creating a heap of size n is actually big O of n and not big O of n log n. And this is a confusion that a lot of people face, because there are thousands of resources that mention that the time complexity for creating a heap is n log n. The time complexity is actually less than n log n, and that's why n log n is not a tight upper bound. it's a very loose upper bound. The actual complexity is around big O of n. Now coming to deletion. Deletion, or more specifically extract operation, removes the min or max element depending on the kind of heap. So what we do is that we swap the root and the value in the last node, and we remove the last node and call heapify on the root. So by doing that, what we are achieving is that when we replace root and the last element, that is a big O of one operation, and we can very easily swap those two. And we know that the root always has the min or max depending on the kind of heap. So when we have replaced those, we can easily extract the last element, and by calling heapify, we will actually take the new root to its correct position. Let's try to understand it better through an example. So if we want to call delete or extract operation on this heap, so what we are essentially trying to do is we are trying to delete 13 from this heap, which is the current maximum element in this max heap. So what we do is that we swap the root and the last element. So when we swap the root and the last element, the heap will look something like this. Now I have told that removing the last element is a big O of one operation in array implementation. So we can assume that we can easily remove the last node, and by removing the last node, we have actually deleted the maximum element. So now the only thing that is left to do is that taking this new root or 4 to its correct position. And for doing that, we can easily call heapify operation. And we know that in heapify operation, what we do is that since it is a max heap, we will replace the we will replace the parent with its greatest child and then call heapify on that child. So right now the greatest child is 10. So 4 and 10 will be swapped, and then we'll call heapify on this child. And since this node will have 4 once they are swapped, and 4 is actually greater than 1, so heapify will stop here. So our heap after heapify operation would look something like this. Now again we'll call delete or extract on this particular heap. So when we call heapify or extract on this particular heap, what will happen? We'll swap the last node and root because we want to extract the root. So for doing that, after doing that, our heap will look something like this. And we know that we can easily remove the last node, so this will be extracted, and then we'll call heapify on the root. So after calling heapify, the root will be replaced with its greatest child, so these two will be swapped, and our heap will look something like this. And similarly, we can keep calling the extract operation or the delete operation and keep removing elements till the size of the heap becomes 0. So now let's try to analyze the time complexity. Swapping the root and last node takes big O of 1 time, and removing the last node also takes big O of 1 time. So the only operation left is calling heapify. So the cost of removal will actually be equal to the cost of heapify. And we have already discussed that calling heapify in a heap of size n will actually take big O of log n time. So the time complexity of whole delete operation is actually big O of log n. Now it is quite clear how this is better than binary tree or an array. So we discussed in the very starting that removal of min or maximum element from a binary tree or an array would have taken big O of n time, and also finding element would have taken big O of n time. So now here we can find the maximum and min element in just big O of 1 time because we need to directly access the root, and removing the maximum and min element is also taking big O of log n time, which is less than big O of n. Now the last part remaining in our discussion is implementation. So to implement a heap, we need to first understand how to represent this heap as an array. So to implement heap as an array, we need to know that if a node is present at index I, so if there's a node index present at index I, then its first child will be present at a node 2 into I plus 1. So if the index of parent is I, then its first child or the left child will actually be present at 2 into I plus 1 index, and the second child or the right child will be present at 2 into I plus 2 index in the array. And also root is always present at index 0. So now if we want to represent this particular heap as as an array, so the array would look something like this. So the array, so this heap has 5 elements, so the size of the array will be 5. So I'll make an array of size 5. 1 2 3 4 5. So the root is always present at index 0. I'll also write the index quickly. So 0 1 2 3 4. So root is always present at index 0. Now the left child will be present at 2 into 0 plus 1, which is first index. So the left child will be present here, and the right child 6 present at 2 into 0 plus 2. So 6 will be present at second index. Now for 10, the left child would be present at 2 into 1 plus 1, which is third index. So the left child, which is 1, will be present at third index, and the right child will be present at 2 into 2 plus 2, which comes out to be 2 into 1 plus 2, which comes out to be 4. So the right child is present at fourth index. So that's how we represent this heap in the form of an array. And we can easily see that how using these formulas we can reach children in O1 time. Also, the above representation was possible just because the tree was complete. And so you can see if there would have been gaps, this representation wouldn't have been possible. Also, one other important thing is that if a child is at index I, so this is kind of reverse of the above formula. So child, if present at index I, then the index of its parent would be I minus 1 by 2. So if this is a child, then the parent would be at this index. So we can move from a parent to both of its children in O1 time, and we can move from a child to its parent in O1 time. So this would come in really handy when we are performing our two operations. This would help us in navigating up and down in just O1 time. Now that we have understood everything, let's write down the code for heaps. So I've already written the code for heap, and I'll go through the code line by line. I thought it'll be easier to explain a pre-written code. That's why I'm not writing it as I explain. Now I have actually written the code for max heap, but the code for a min heap will also be very similar. You can probably try to write down a code for min heap on your own, and then you can try to run that code using some example and see if the code is working fine. So yeah, let's quickly go through the code. So this is the class which represents the max heap. So it's I've defined a max heap class, and there are two data members. One is the size and the other is the heap itself. So this heap vector will basically be storing my values, and size is nothing but what is the current size of the heap. So now let's quickly move to the different methods which are present in this particular class. So first method is your constructor, the public constructor, and it is a default constructor, and it is nothing but it just initializes the size as 0. So when we are initializing a heap, there will be no element in the heap. So what we have done is we have initialized size as 0. So the next three methods are nothing but helper methods. So they take the current index as input and return the index of the parent, the left child and the right child. So if the current index is I, then the parent, as we have already discussed, is represented by I minus 1 by 2. If the current index is I, then the left child is 2 into I plus 1, and if the index is I, then the right child is 2 into I plus 2. So these three methods are nothing but helper method which return the value which return the index of parent, left child and right child. Now next method is basically the get method to get the maximum value of our collection. So we know that in a max heap, the max value is always present at the root, and we have already discussed that in the array representation of a heap, root is stored at index 0. So when we have to extract the, or not extract, just get the max element, what we do, we first check that if the size of the heap is 0 or not. So if the size of the heap is 0, then obviously there is no element, you cannot return anything. So I've just returned int min, which is basically an indicator saying that there was no element. So I have kept it as a junk value. Wherever I had to return a junk value, I've returned int min in this code. You can return an exception or maybe any value based on your choice. And in case if it's a valid query and there are elements present in the heap, then our root will be present at the 0th index. So we have returned the element at the 0th index. So this line basically returns the element at the 0th index, which is going to be the root, and also which is going to be the maximum element. Now in our discussion, we discussed two main operations. In the first operation, what we do is that we move root to its correct position. So we assume that root is not present at its correct position in the heap and all other nodes are there at their correct position, and we recursively take root to its correct position. And the second operation, what we do, we take last node to its correct position in the heap. So the first operation where we take the root to its correct position, I have named that operation as downheapify, because if we see that if we visualize our heap as a tree, so what we are doing in the first operation, we compare the current node with the left and right child and then swap accordingly and delegate the task to the child. So what we are doing actually is we are moving down in the tree. So that's why this operation has been named as downheapify. Similarly, in the other operation, what we are doing is that we are comparing the current node with its parent, swapping it and delegating the task to the parent. So again, in the tree visualization of the heap, we are moving upwards in the tree. So that's why I have named that operation as Upheapify. So let's quickly go through the code for both the operations. Now let's recall what we were doing in the first operation. So we were getting the index of the current node and we were comparing the value of the current node with its left child and its right child. If the value of the current node was greater than both the children, so in that case we did not have to do anything. The node was at its correct position in the heap and then we can end the operation there. In case if it was not the greatest value, then what we did was we swapped that value with the greatest child and delegated the task to that child. So by doing that, we would eventually take the node to its correct position in the heap. So that is what we are doing in this code. So our current index is represented as int I, which we have received as the parameter to our method. Then we get the index of the left child for this index. We get the index of the right child for this for the current index I, and again int index. So this variable int index is basically storing the index of the greatest element. So right now we have initialized this index or this variable with the current index, but this variable will be eventually storing the index of the greatest value. So this will be updated in the next two conditions. So here we check that first the index of the left child that we have got should be within the limit, should be less than the size of the heap. So it should not go outside the bounds of the heap. And we check if the left child is greater than the element itself. So in this kind, so index right now, which will eventually hold the index of the greatest element, right now it is holding the index of the current element. So here what we are checking is that whether the left child is greater than the current element. If it is, then we update the value in the index variable. We store the index of the left child in the index variable. Now again for the right child, if the index of right child is within the bounds of the heap, and if the value of the right child is greater than the value of the current element or the left element. If the current element was greater than the left child, then this index would be holding the index of the current element, otherwise it will be holding the index of the left child. So depending on which was greater, the value of index would have been updated. So we check that if the right child is greater than both of these values. If it is so, then we again update the index, otherwise we don't update it. So eventually index will be holding the value of the greatest element among these three elements. Now if index is equal to the current index, then obviously the current element is the greatest element and it is at its correct position, and we do not need to do any operation and the operation can end. In case if it is not the current index, that means that it will be equal to the index of left child or right child. So in that case we swap the child, whichever child it is, we swap it with the current element, and then we call the same method because it's a recursive method, we call it on the child. So now we have swapped the element and we have delegated the task to the largest child, whichever it was. So let's quickly move to the next operation. Here what we have done, here the current index is being represented by int index parameter. So first what we do is we get the index of the parent for this current element. So we have called our helper method parent, which gives us the index of the parent. Now we check that whether the current element is greater than the parent. If the current element is greater than the parent, obviously these two should be swapped, because always the parent is going to be greater than both of itself, which is the heap property of max heap. So in case if it is not, then obviously this operation can end here. We do not need to make any recursive calls, we do not need to delegate the same task to the parent, no swapping is required, and the operation can end here. If in case it is not, then we swap the parent and the current element, and we recursively call the same method Upheapify on the parent, because the parent also needs to check that whether it is smaller or greater than its own parent, and accordingly move up in the heap. And now what would be the base condition for this recursive function? Basically, once we have reached the root, if we have reached the root, obviously root will have no parent, so we cannot swap root with its parent. So once we have reached the root, we have climbed to the top of the tree and we do not need to continue this operation. So that is going to be the base condition, and then we have basically returned from there because we do not want to continue the operation. Now we will use these two methods, Downheapify and Upheapify, in our next two operations, which are going to be basically insert and delete. So now since we have understood Upheapify and Downheapify, insert and delete are actually very simple. So also I'll explain the delete method before the insert method. So in the extract or the delete method, what we do is that we remove the highest element of the max heap, and highest element is obviously at the root, so whatever element is at the root, that will be removed from the heap. So first obvious step is we check if the size of the heap is 0 or not. If the size of the heap is 0, obviously we cannot remove anything, so we just return. So here in normal case there could be an exception or any junk value returned, or whatever indicator you want to return to your main or driver method. In case if the size of the heap is greater than 0, then we can remove the element, and we know the strategy for removing the element. We basically swap the last element and the root element, and after swapping the last element and the root element, we simply remove the last element in O1 time and then call Downheapify method on our root. So that is simply what we have done. So these three lines basically swap the last element of the heap and the root. So last element would be present at size -1 in this vector obviously, and the root is always present at 0th index. So we have swapped those two elements. Now what is the method to remove the last element of the heap? So here in this particular implementation, what we are doing is that we just stop tracking that element. We are not actually removing it from the vector, we just stop tracking it. We just assume that it has been removed, because if we reduce the size of our heap, the last element will always be present at size -1. So what we have done is that we have automatically stopped tracking that last element. So down the line that element might get replaced with any other element, or anything can happen with that element, but we have stopped tracking it as part of our implementation. So after swapping, after removing the last element, what we have done, we have called Downheapify method on our root. Now coming back to the insert method is also pretty simple. Now now the parameter for the insert method is the value that needs to be inserted. So the first obvious step is that we increase the size of our heap by 1. Obviously if we are going to add one element, the size of the heap will going to increase. Now the thing that is that might be a little confusing with that implementation where we are using a vector and all. So what we saw in the extract method is that we are not actually removing the element, we have just stopped tracking it. So now if the new size is actually greater than the already existing size, what does that imply? It implies that we were tracking all the elements in the heap, and now a new element needs to be added as a new cell in this vector. There was no element which were already present there which were in the untracked state. So what this says is that, I'll take an example. If we had a heap which had elements say 3, 2 and 1, so our size pointer was here. So actually this size pointer was equal to the size of the heap. So that implies that we were tracking all the elements. If this size vector, if this size pointer would have been somewhere behind it, that would have implied that we are not actually tracking this last element, and this last element can be replaced with any value. This is just a junk value. But in case if we are tracking the last element as well, we need to add a new cell. So that's what we have done, that if the pointer was at last cell and after size plus plus it is actually greater than heap size, so we add a new cell, and this new cell will contain our value. But in case if it was smaller than the size, then that implies that there were some elements which were not being tracked. So we can, if they were not being tracked, they can be replaced with the new value. So in the else statement we have replaced the old elements with the new value. And simply what we need to do, we need to call Upheapify on this last node, because all other nodes are in their correct position, just need to take this new node to its correct position. So that's what we have done, we have called Upheapify on this last node. And that's all. We have completed all the operations in the heap, and towards the end we just put a closing parenthesis and a semicolon. Now you might be wondering that every time I need to use heap, will I write this boilerplate code? No, actually every language has a container implementing heap. In C++ STL library, we have something known as a priority queue. And this priority queue container mimics the max heap. So this particular container has three operations: push, top and pop. So push basically adds an element to the heap, top returns the greatest element, and pop removes the greatest element. So pop is basically extract or deletion, push is insertion, and top is just accessing the greatest element in O1 time. So I'll be using priority queue for the subsequent problems that we are going to solve. If you code in some other language, probably you can go on Google and search that what is the inbuilt implementation of a queue, inbuilt implementation of a heap, and then use that particular implementation or library. So finally we have reached the end of this video. We have discussed quite a lot of things, and in upcoming videos we will learn how to judge if heap will be of any benefit to solve the problem, and then how to use it to actually solve the problem. So hope to see you in the next video of the series. Till then, take care and keep learning. Bye bye.